Hello friends, today we'll be going through the design of canals. So in design of canals, we have the two design canals parameters. That is, we can design canals through non-alluvial channels. Likewise, we can design canals with having alluvial channels. Okay, so the canals flowing through the non-alluvial soils is non-alluvial canals, and the canals that are flowing through the alluvial channel or source or soil is the alluvial canals. So these are the two things we will be dealing here, and at first we will be going through the design of canal through non-alluvial canals. Okay, so before heading to this video, always remember that failures inspire winners and defeat losers. This is the line I have been motivated, and this is the line from the book called Rich Dad and Poor Dad. So if you are new to this channel, you can like, share and subscribe this channel as well. Friends, first we will be going through the design of non-alluvial channel or canal. So at first, before designing the non-alluvial canal section, first of all, we need to know what is non-alluvial canal. Okay, so non-alluvial canals are those canals in which the canals are passing through the non-alluvial soils. Okay, so you have the mountainous regions that may undergo the disintegration over a period of time, forming in a rocky plain area. So such a rocky plain area is called non-alluvial areas. So these non-alluvial areas have uneven topography and the hard foundations. And the river passing through such canal has no, river passing through such areas has no tendency to shift their course. So thus, the canal passing through such areas having non-alluvial areas having uneven topography and hard foundations are called the non-alluvial canals or channels. In these canals, there is no problem of silting, and thus they are known as stable canals. So friends, before designing the non-alluvial canals, we need to know the flow equations. So we have two flow equations. One is Chezy's equations, another is Manning's. So at first we will be going through the Chezy's equations. Now Chezy suggested that the velocity through the canal V can be written as V equals to C under root of R times S. So here C is the Chezy's constant and R is the hydraulic radius and S is the bed slope. So here hydraulic radius R can be determined by A by P, so weighted area by weighted perimeter, and S is the bed slope. That is, we know that before designing the canal, we know that what is the bed slope of the canal. Okay, so the unknown is the Chezy's constant C. So the Chezy's constant C can be determined by two formulas. One is the Benz's equations, second is the Cotter's equations. So Benz suggested that the value of Chezy's constant C can be determined from C equals to 85 divided by 1 plus K by root R, where R is your hydraulic radius and K is the benzene constants. That is, value for a good channel is taken as 1.2 to 1.4, and for the channel in a bad conditions, the value of benzene's constant can be taken from the range of 1.7 to 1.8. Likewise, the Cotter's equation can be helpful for determining the Chezy's constant C, where C can be determined by using formula as C equals to 1 by n plus 23 plus 0.00155 divided by S whole divided by 1 plus 23 plus 0.00155 by S bracket n by root R. Here R is, you know that R is the hydraulic radius, S is the bed slope, and N is the constant known as the Cotter's coefficient. Now friends, the second flow equation is the Manning's equations, in which the velocity through the canal can be determined by V equals to 1 by N into R2 by 3 S1 by 2, where R is your hydraulic radius, S is the bed slope of the canal, and N here is the Manning's coefficient. So these two are the flow equations from where you can determine the flow parameters like velocity, discharge, area, weighted parameters, hydraulic radius, all these things. Now we will be going through the design procedures of the non-alluvial channels. So here we listed out the different design procedures for the design of non-alluvial canals. Here at first we need to choose approximate value of the maximum permissible velocity and the side slope on the basis of type of soil. So first of all you need to assess what is the type of the soil that is available for the canal construction in the non-alluvial channels, and on the basis of that you need to select the maximum permissible velocity. So you need to select that velocity that could not erode the canal material. So that should be safe maximum permissible velocity, okay? And on the basis of side slope you need to select the two parameters here, maximum permissible velocity and the side slope. Likewise, then you need to determine the area of cross section of the channel. So you can determine the area of cross section of the channel using discharge formula, that is the continuity equation. You have discharge equals to the area of cross section area into the velocity of that section, okay? Now after finding the discharge, you can determine the hydraulic mean radius using the Manning's equations. So you already know that the Manning equations in the flow conditions. So you can use these flow conditions. You can also use chezy whenever what are the parameters that you have available for that particular canals. On the basis of that you need to assess which flow equations you are using there. So when you have the ability of the Manning's constant, then we use the Manning's formula. So discharge equals to 1 by n AR to the power 2 by 3 times S1 by 2 is the discharge formula for Manning's equations. Now you have determined the hydraulic radius. So you can determine the weighted parameter here. The weighted parameter P can be determined here. So by the formula hydraulic radius R equals to A by P. So if you just substitute and change the values, cross multiply it, you will determine the value of the weighted parameter. So you have determined the area of cross section, you have determined the hydraulic radius, so you can easily determine the value of the weighted parameter. Finally, knowing the values of cross-sectional area and weighted cross-sectional area and the perimeter, you can determine the bed width and the depth of the channel. So our main aim is to determine what is the bed width of the channel and what is the depth of the channel. So on the basis of all these above parameters, you can easily find out the bed width and the depth of the channel section. So whatever channel you take, so sometime it may be a rectangular, or mostly it is trapezoidal section. So in the trapezoidal channel, you can determine the bed width and the depth of the canal or channel section. So this is the design procedures. Now we have the numerical portion of the design of non-alluvial canals. So for the designing of this canal, generally the discharge and the slopes are known. Okay, so we will be available before designing. We need to know the parameters like discharge and the side slopes. We'll be knowing. So we are presented a problem that discharge is 50 cumac. The Manning's coefficient n is 0.0225 and the side slope is 1 in 5000 and the base width to depth of the channel ratio is given as 6. So using this data available, you need to design the non-alluvial canal or channel. So friends, let us see the solution of this problem. Now friends, we will do the solution. Here given in the question that discharge is 50 cumac, that is 50 cubic meter per second, and the side slope is, sorry, bed slope is given as 1 in 5000. So we are given that the bed slope is the 1 in 5000 and Manning's coefficient is given as 0.0225. So using the Manning's formula, we have discharge equals to 1 by n AR 2 by 3 S 1 by 2. So here we can see that the value of the formula of hydraulic radius R can be written as ratio of the weighted area by the weighted perimeter A by P. Okay, so solving this, we can obtain discharge equals to 1 by n area to the power 5 by 3 weighted perimeter to the power 2 by 3 into the side slope to the power half. So this is the expression. So here we can see that the area, weighted area and the weighted parameters are unknown here. So we need to assess which type of the channel is and what is the parameter. So what is the parameters of that channel? So in this case, let us assume that as a trapezoidal channel. Okay, so we shall assume a trapezoidal channel here. So friends, for the trapezoidal sections as shown in the figure, the weighted area can be determined as shown in the figure. That is, we have the weighted area. So if we take this trapezoidal section, you can see that this weighted area can be the sum of the two triangles, area and the sum of this rectangle. So the rectangle's area is B into D and the sum of these two rectangles, that is, sorry, sum of these two triangles is 2 into 1 by 2 is the area of individual triangle, 1 by 2 into the base is Z times D into the height, that is D. So if you solve this, you will easily obtain the area of the weighted area of the trapezoidal section as BD plus ZD square. Likewise, we need to assess the weighted parameter P of this trapezoidal section. So the parameter can be easily obtained if we add all the entire sections of weighted of the trapezoidal canals. Okay, so this base is B. If we add the two triangular portions, so if we add these two inclined portions, then we'll obtain the value of the weighted parameter. So this inclined portions, so if you can use the Pythagoras theorem as, so you can use the Pythagoras theorem and easily obtain that this hypotenuse is D times 1 plus Z square. So this D times 1 plus Z square is in both sides of this trapezoidal section. So the total weighted parameter can be P equals to B plus 2D 1 plus Z square. So the weighted parameter is B plus 2D 1 plus Z square and the weighted area is BD plus ZD square. So one thing you need to know. So this is the major thing you need to know. So you can easily derive from this figure. And we have assumed that the side slope of the canal is Z used to 1. Okay. So that is Z horizontal to 1 vertical. Okay. So if you're going to Z horizontal distance, then you are taking 1 vertical. Okay. So this is the assumption. Now friends, as we have determined the discharge relation as 1 by n, A 5 by 3, P 2 by 3 into S 1 by 2 as in our previous expression. So here we need to know the area and the weighted area and the weighted parameter. So A is given as BD plus ZD square. So if you substitute the value of B as 6D, because B by D ratio is given as 6, so B equals to 6D, you can substitute in this expression. And if you assume that Z equals to 1, that is Z horizontal equals to 1 vertical, assuming the horizontal distance to vertical distance ratio is 0.5 used to 1. So we are assuming this is a cutting section. So 0.5 used to 1, we assume the Z used to 1 ratio. Okay. So if you solve this, the weighted area can be given as 6.5 D square. So likewise, the parameter can be given as P equals to 2PB plus 2D1 plus Z squared. So if you substitute Z equals to 0.5, and if you solve this, you will obtain the value of parameter P as P equals to 8.236 D. So this is the value of the parameter, weighted parameter, and the weighted area as 6.5 D. So you need to substitute this value of A and P in this expression so that everything in the expression will be in the term of D. So you can easily solve out the problem. Now friends, you can substitute the values of area, weighted area and weighted parameter here, which are in terms of D. So if you just substitute it, you will get discharge is 50 equals to 1 by n is 0.0225. And if you substitute the value of area, weighted area as 6.5 D square and P as 8.236 D, and if you substitute the side slope as 1 in 5000, so solving this you can easily obtain, so you can easily obtain d8 to the power, so d power 8 by 3 equals to, so that expression. So if you can solve this, you can easily obtain the depth of the trapezoidal canal as 2.71 meters and the base width as 16.26 meters, that is B 6 times D, and if we solve this we will obtain B as 16.26 meters. So this is the way you can just solve it. You can directly use the calculators for fast solving. So I have shown a large method for solving, so you can easily use the calculators to solve here. So at last you can just write the design criteria, that is what are the things that you have obtained, that like the base width as 2.75. So suppose you obtain the base width as 2.75 meters, we have just increased it to whole numbers. Okay, so just for easy way, for doing easy, we just increase it. And the depth as 16.30 meters, side slope Z used to 1 as 0.5 used to 1, and the trapezoidal canal sections. So this is the design considerations that you have obtained from the following data sets of data.
So friends, if you find this video as useful, you can like and share to your friends. And for such videos, stay tuned to this channel. Thank you. We will meet soon in another video.